All right, so we're now recording. I want to introduce Tom Mallouk today. Tom is the Evan Pugh University Professor of Biochemistry and Molecular Biology, Physics, and Engineering Science and Mechanics. He is also the Department Head for Chemistry at Penn State, and he's the Associate Director for the Penn State MRSA. He's also on this 2DCC grant, faculty working on bulk synthesis of chalcogenides. So without anything further, Tom, please go ahead.
Okay, thank you very much, Kevin, and thank you everybody for coming. This is a really good-sized group. Maybe the lunch had something to do with it, but thank you for coming anyway. So this is kind of part two of the webinar about bulk synthesis, and which we heard already from Dave Snyder, who talked about how we make crystals of 2D materials in the 2DCC. And what I want to talk about is how we take those things apart into few layers and single sheets, and to a smaller extent, what we can then do with those materials after they come apart. So why would we want to do this? Well, many of you who work on 2D materials know that they have a broad variety of interesting physical properties, right? And those are some of the reasons we're interested in them. We're interested in their electronic transport properties, their optical properties, etc. But there are also properties that are important for these things as bulk materials. So, for example, some of the layered oxides. Any of you have a cell phone, you have a layered oxide in there that's storing the energy in your lithium battery. There are applications in membranes, applications in separations, etc., and in lubricants, etc., composites that involve bulk quantities of these materials that things you just can't do with a single sheet. So our involvement over the last few years, especially in this area, has been to figure out how we can take these things apart and take them apart without doing a lot of chemical damage to them, especially. So now different classes of these materials have different chemical strategies for intercalation and exfoliation. In one category, we have graphene, boron nitride, and related materials that have pi-bonded sheets separated by a van der Waals gap. And then we also have layered chalcogenides that are typically, again, bonded chemically in 2 dimensions and then have a van der Waals gap between layers. Both of these categories are van der Waals solids, and these are different in terms of the chemistries we use from this broad class of materials called intergrowth structures. In intergrowths, we have typically 2 kinds of crystal structures that repeat over and over in the lattice. In the one I'm showing you in this picture, this is a layer perovskite in which there are layers of bonded metal oxygen octahedra or metal fluorine or metal nitrogen octahedra interleaved with a salt layer. But these intergrowths, the chemistry is quite diverse here. And there are different strategies we'll see for opening up the layers and exfoliating these. Okay, so this exfoliation has been around for a long time, and this in the graphite business, this predates by a long way actually the discovery of the interesting electronic properties of graphene. And they're basically historically 2 ways into taking graphite, this van der Waals solid of pi-bonded sheets, and pulling the layers apart. One way is to use a strong reducing agent, like an alkali metal, potassium for example, and to wedge the layers open and intercalate, and that, as we'll see in a second, that is driven energetically by a redox reaction. And then one takes a solvent, and this is a reactive solvent in this case, that then converts the material back into graphite. You can also do this oxidatively with strong 1-electron oxidize the sheets and put carbon-oxygen bonds in between the sheets. And then these can be reduced back to something that looks like graphene. But basically, when you do this, both the strong reducing agents and strong oxidizing agents cause permanent damage to the sheets. And the graphene never gets back to the way it was. Okay, the high mobility of electrons and holes in graphene means that carriers can, if there's a defect somewhere, the carrier will know about it. And so this kind of damaging mixture of strongly oxidizing acids, for example, that we use to make graphite oxide out of graphite, does a lot of damage to the carbon network and to the electronic properties. Now, why do we need such strong oxidizing and reducing agents to open up the layers in graphite? So this has been understood for an awfully long time. In fact, the chemistry of graphite, the intercalation chemistry of graphite, goes back to the middle 1800s. This first paper by Brody actually claimed to make graphite oxide with oxidizing acids. And in the intervening more than a century and a half, this has been well studied. This slide shows an excerpt from a paper from 1938 by Rudolph, who studied the intercalation of graphite by oxidizing and reducing agents. And he proposed a Born-Haber cycle that could explain why you need such strong oxidants and reductants. Basically, you have to open up the layers, break all these van der Waals contacts. Then you have to do a redox reaction. Let's say in this case it's oxidation of graphite, so there's an ionization event here. Then you have some intercalant that's a strong oxidant, so it has an electron affinity that partially offsets the energy that it takes to take that electron off. And then finally you get some energy back in terms of this lattice energy of the ionic lattice. And this was studied for many different oxidants and reductants, and there's a threshold of oxidizing or reducing power that's needed to oxidize graphite. And for boron nitride, the situation is even worse because layer boron nitride is a semiconductor, and that means that you have to do some extra work to take the electron out of boron nitride. It's harder to ionize than graphene. So, in fact, in the literature, there's only one example of an outer sphere oxidant that can take electrons from boron nitride and produce an intercalation compound. That's this very powerful oxidant, S2O6F2. So, and again, these reactions do damage to the layers because of these strong oxidants. So, when we started on this, we were interested in working particularly on boron nitride, and we had done some work. My research associate Nina Kofyakova had done work on this strong acid mixture for producing graphite oxide out of graphite. And I asked Nina if she would try this reaction with boron nitride. And she said, no, this is not going to work. You know about that energy level diagram for boron nitride. I said, please humor me, give it a try. So she did, and what she found, surprisingly, was that this mixture of acids did actually produce a first stage intercalation compound of boron nitride. And then she took away one reagent at a time to see what was the actual intercalating agent. And it turns out all you need actually is a Bronsted acid. So phosphoric acid is good enough to intercalate layer boron nitride. Now, the reason this hadn't been discovered and this also works for graphite, the reason it hadn't been discovered in the over 150 years of people throwing graphite into acids is you have to do it in a very special way. You have to use neat phosphoric acid, and you have to evaporate the phosphoric acid in order to break up the hydrogen bonding in the liquid and that's when the intercalation happens. But this is kind of interesting because this works for BN through you might expect an acid-base interaction with the basic nitrogen, but also with graphite, which has a very polarizable pi electron sheets. And so you can make first stage intercalation compounds with both. We worked with Yuanqi Wang and Vin Crespi to understand how this worked. They did electronic structure calculations to show, for example, in the case of graphene, how the pi electrons polarize themselves to create this favorable electrostatic interaction with the polar phosphoric acid group that intercalates. So this is one way in. I'll tell you how we go from intercalation to exfoliation here. But there's another method that's very interesting and very general that was first developed by John Coleman's group, where you don't need a strong oxidizing or reducing agent. With just about any van der Waals solids, you can exfoliate the material simply using solvent, an appropriate solvent with either sonication or mechanical shear. And the idea here is these van der Waals solids have this strong van der Waals attractive energy between layers. But if you choose a solvent that has van der Waals parameters that are very close to that of the sheets, then the dissolved state of the nanosheets energetically isn't very different from the stack state because the solvent is interacting with the layers. And so solvents of intermediate polarity tend to be pretty good for this, and you have to provide the activation energy for this to happen with shear or with exfoliation. So this is terrific in terms of making nice sheets that resemble those you can make by mechanical exfoliation, let's say of graphite to graphene. But unfortunately, the yield of single sheets is quite low. That is, you get lots of few layer composites, but you don't get very many individual sheets. Part of this issue may be that when you think about this van der Waals term holding the van der Waals energy holding the sheets together, if you have an infinite stack, that energy can be a little bit less per layer than if you have a bilayer or trilayer, where the bonding is directed towards the encapsulated sheet. So with this method, you end up mostly with few layer materials. But if you combine this with intercalation, then you can actually get mostly single sheets. So with BN and with graphite, Nina was able to show that you get lots of single sheets. And in fact, if you choose the solvent, this work is still not published, but if you choose a solvent appropriately, you can get the yield of single sheets of graphene to be nearly quantitative. And for BN, something like 80% of it is single sheets with the right solvent. And this is with very gentle mechanical agitation. So this is just intercalating with phosphoric acid and then stirring with just a magnetic stir bar for a few days. You get to single sheets of graphene. We started to characterize these. So this is work Nina did with Nestor Perea in Mauricio Tirone's group, where they're able to take graphene ribbons that are exfoliated this way, and first look at the Raman spectrum, which shows essentially pristine graphene, and also to look at the electronic conductivity of these strips, which is much higher than one gets with reduced graphite oxide. So this stuff really does look like graphene, both physically and electronically. Okay, now with the, this is a slide I stole from, thank you Josh Robinson's website. Yeah, I think you have the best periodic table of layered chalcogenides on your website. So with the layered chalcogenides, there's this huge diversity of van der Waals compounds one can make, as well as so with all kinds of interesting properties like semiconductor, ferromagnet, anti-ferromagnet, topological insulator, etc., and a variety of structures that one can access. But this is a different animal in terms of intercalation and exfoliation. The Bronsted acid trick doesn't seem to work on these materials. Rather, what you get is a lot of, in the case of sulfide, you get a lot of H2S and other stuff you don't want. The way to do this, there is has been known for a long time a redox cycle that will intercalate lithium or other alkali metals in between the sheets of the layered dichalcogenides, and then typically a reaction with water or with a polar organic solvent to generate suspended single sheets, and the other product of this reaction is an alkali hydroxide. Now again, this cycle, this redox cycle, damages the sheets in one or more ways. So one problem is in this reaction you're generating a lot of this strong base that eats away at the mostly at the edges of the sheets, but also at the basal planes. And secondly, the intercalation reaction involves reducing, in this case, MOS2 from molybdenum-4 to molybdenum-3. When you do that, this is no longer happy in the trigonal prismatic coordination of molybdenum-4 and shifts to an octahedral coordination of molybdenum, going from this 2H phase to this metallic 1T phase. And again, this never really goes back to where you started. So if you want these materials in pristine form as good semiconductors, let's say for making a device layer by layer, an electronic device, this isn't a good way to go. The question we asked recently, though, is, again, thinking about this Coleman method for gently exfoliating materials and doing intercalation that doesn't involve a strong redox cycle. Instead of using one equivalent of butyl lithium, which everyone has used since 1986, what if we just used a little bit? So it turns out that if you look at different stoichiometries of butyl lithium to MOS2, at the beginning it looks like really nothing is happening. If you look at the X-ray diffraction pattern of the material with, say, 1/10 of an equivalent of butyl lithium. And if you look at the XPS, there's also not a big change at this stoichiometry. The metallic form of reduced MOS2, you can actually see pop up as shoulders in the XPS when you get to more like 4/10 of an equivalent. But at 1/10 of an equivalent, it looks like nothing has changed except this primary layer line seems to broaden a little bit to low angle, meaning that some of the material is puffed up a little bit. There's a little bit of disruption of the layers going on. And what we think is happening here is, it's known that intercalation, of course, with a layered material starts at the edges. And this may just represent ruffling those edges a little bit. And once you have them ruffled now, the mechanical shear or sonication method then works quite well to take the material the rest of the way apart. So in this case, this is with MOS2 with 1/10 of an equivalent of butyl lithium. Predominantly, what you get are three-layer multi-layers, and a nearly quantitative exfoliation to that tri-layer stuff. And we're still working on this with different stoichiometries and other TMDs to see if we can see what we can do in terms of making bilayers, single monolayers, etc. This is work that was done by Xiaobin Fan when he was here for a sabbatical at Penn State a year ago. Okay, so now moving to intergrowth structures, there's a pretty big variety of intergrowth structures that have in them nanosheets as part of their structure. So, for example, calcium silicide is, this is stuff you make by just reacting the elements, and the crystal structure consists of puckered, six-membered silicon rings, all bound together, and in 2D interleaved with calcium ions. By exfoliating these things in a two-step process involving coordinating amine and acid, you get these sheet-like things that, under certain conditions, basically give you a stoichiometry of Si6H6, where the silicon sheets are capped with hydrogen. This is not a very stable form of the material, but it can be capped chemically with different reagents that will then put aliphatic or aromatic capping groups on the silicon sheets. You can do this with silicon or germanium. And other layered solids, these are MAXenes. Okay, they are typically transition metal carbides, transition metal borides that have in them a main group element like aluminum, and that aluminum can be etched out with hydrofluoric acid, leaving the two-dimensionally bonded sheets of, in this case, titanium carbide. This is work from Yuri Gagazzi and Michael Barsum at Drexel, and they can get a range of these kind of nanostructures where they typically will have multi-layers of this stuff that is where the aluminum is etched away. So in this case, the exfoliation chemistry is pretty forcing, usually involving strong acid and etching away part of the structure to give you your nanosheets. Another class of intergrowths that is much more user-friendly in this way are the intergrowths of transition metal oxides with alkali or alkali earth metals. So these are titanates, niabates, titanoniabates, but also tantalates, tungstates, etc. And there's a very rich variety of these structures. Most of these structures are derived from the three-dimensional perovskite structure by shearing some of the layers. And they are very adaptive structures. So with almost any stoichiometry you put in the tube of transition metal oxide and alkali oxide, heat them up, you end up getting one of these layered oxide structures. Here, the way into the chemistry of intercalation and exfoliation, if you have low charge density between the sheets, typically with alkali ions between the sheets, you can replace those with protons, as I'll show you in a second, and then that's the way into exfoliating the material. These are also interesting materials in terms of topochemical reactions. So, for example, this structure, KTI NBO5, if you replace the potassium ions with protons with an acid exchange, and then heat the material up, the octahedra, the sheets slide over and the octahedra eliminate water to bond one to the other in a topochemical way. So these things just zip up and make new structures that you can't actually make directly from, say, titanium, niobium, and oxygen. For example, the synthesis of TiO2b, another polymorph of TiO2, starts with a compound that looks just like this, a protonated layer titanate with that topochemical reaction. This is easier to visualize and to see with these simpler structures. These are layer perovskite structures, where we have blocks that consist of the three-dimensional ABO3 or ABX3 perovskite interleaved with salt layers. So in this case, this Relison-Popper stoichiometry would have the perovskite structure interleaved with something that looks like the sodium chloride structure. So metal, oxygen, in octahedral coordination here. You can also have an intergrowth where there's a Bi2O2 layer. Those are called Aurevillius phases, or where the charge density on the sheets is lower, and you have half the density of alkali ions. These are called Dion-Jacobson phases. And then you can have a variable number of these octahedras stacked up, 1, 2, 3, 4, etc. So again, these are intergrowth structures, and the chemistry you can do, there's specific chemistry for all these interlayer, everything you can put in the interlayer. And in fact, we showed a number of years ago that one could transform by ion exchange methods many of these intergrowths from one form to another, back and forth, for example, to the Aurevillius phase. This was work by Sugimoto, etc., company in Japan, but also to go from the Relison-Popper form to the Dion-Jacobson form, and then to topochemically turn these into three-dimensional perovskites. A very versatile chemistry here. In the context of exfoliation, though, the most important reaction is simply acid exchanging out the alkali ions and then doing an acid-base reaction in which we have a strong base reacting with this weak acid solid that forces the cation that comes with the hydroxide in between the layers. And if this is a large cation, those layers become spread apart enough to where they can exfoliate easily. And so this can be a quantitative process in which you start with a pound of this alkali transition metal oxide that you just make from combining the elements or the suitable precursors at high temperature. You can grow crystals of these things, and then you can take them apart, take a pound of this apart to make a pound of exfoliated nanosheets in quantitative yield. This reaction, which has been around for a long time, actually the reaction of amines or quaternary ammonium hydroxides with layered acids, is only beginning to be, or just recently, well understood from the kind of physical chemistry perspective. So these are some really beautiful experiments that were done by Fengxia Geng and her advisor Takeyoshi Sasaki at NIMS in Japan, where they showed in this very elegant experiments with these layered titanates that the thing that's really driving this exfoliation is an osmotic swelling effect, in which this inner layer basically is full of salt. You've got these large cations, and they're counterbalanced by the sheets, which are anionic. If the surrounding medium is low in salt, then what will happen is you'll have an osmotic driving force for bringing more and more water in between the layers. So at low salt, you actually see these beautiful interference colors develop as the layer spacing becomes some fraction of the wavelength of light. And they also see this in terms of you can see this visually in terms of taking a constant amount of this stuff and varying the concentration or the amount of the exfoliant At the beginning, you need enough of it, of course, to exchange away some of the protons. But if you add too much, then you have high salt out here in the solution. This osmotic effect is less, and you don't get as much swelling of the layers. So the chemistry, if you like, the physical chemistry and the thermal chemistry of this is only really now just beginning to be understood just a couple of years ago. Okay, once you have these layers apart, you can, we see these lovely cartoons of heterostructures of things you might want to build from 2D nanosheets. And how do you make those? So one way to make them is simply to, if they're charged, like these oxide nanosheets, is to absorb them layer by layer on charged surfaces. So this method, this layer by layer assembly, was first developed for polymers, polyanions and polycations, but it works very nicely with nanosheets. So instead of using spaghetti to make a layered nanocomposite, you can make a lasagna using exfoliated nanosheets. And if you've ever eaten a lasagna, you know that the structure is maintained through various chopping operations, etc. And the layers don't mix quite so much as if you do this with sticky spaghetti. So again, one can use this acid-base technique with a variety of starting material solids to make these anionic sheets that are capped by these easily displaced large cations, and then do this layer by layer assembly, in this case with alternating with polycations, like polydiallyl dimethylamine. And what I'm showing here is a TEM picture of these nanosheets and also an AFM of the assembled nanosheets. And you see under the right conditions, they will tile, they're irregularly shaped, but they'll tile the surface very, very densely because when they adsorb, obviously they have some mobility on the surface and they can find a very dense tiling. So one can make multi-layers this way, and this is ellipsometry showing a thickness after each dip in the anion or cation solution, and very controllably make one sheet on top of another. And then these things can be sintered or chemically etched to remove the organic component and just leave the inorganic material. Now, a little sidetrack that we went on with this was I had a visitor come to my lab from Shiseido. This is Hideo Hata. He came from Shiseido, and you probably know Shiseido is a cosmetics company, and they were interested in a lot of their makeup is made with using clays as the base for, say, rouge and for eyeshadow and stuff like that, where you have to spread this on the skin, and you need a van der Waals solid that can, has good physical properties, but they also would like to put stuff in it, for example, dye molecules. Now, with clays and most layered oxides, the situation is the sheets are anionic, and the stuff in between the sheets is cationic. So this works perfectly fine if what you want to put in between the layers is cationic. That's easy to do. But if you want to intercalate an anion, and many of the dyes they're interested in are anions, this doesn't work. But what we thought about was this layer by layer assembly that we developed a few years earlier. And the reason that this stops at one layer each time is not because we exactly charge compensate the layer underneath, but rather that we overcompensate that charge. That is, here this monolayer has underneath it a polycation film. And when the anionic nanosheets adsorb, more negative charge adsorbs than the positive charge we initially had there, and that prevents any more of the negatively charged sheets from adsorbing. because now the surface is negatively charged. So we thought about that charge inversion, which is what we were trying to do here. And one way to do this is to, if you just choose intercalating polycations that are poorly matched in terms of their charge density to the charge density of the sheets, then they have to loop around to get in there, and they bring with them some extra anions. And then those extra anions become exchangeable, and this thing kind of becomes like an accordion. It'll let in anions of a certain size but no bigger. And so this actually worked. So Hideo was able to make this clay intercalation compound, for example, with a nice blue dye that you might want to use for some edgy eyeshadow or something like that. And then what was really sexy, I think this is too expensive for makeup, was a lot of inorganic colloids are also negatively charged, like gold nanoparticles. So you can intercalate gold nanoparticles and make this, pink stuff that contains gold. If you really want a great gift for somebody, it would be, some rouge that's got this gold in it. So anyway, Hideo was having a lot of fun with this, looking at all kinds of inorganic nanoparticles that could intercalate. And what happened was something unexpected. So what happened was when he got to, he was studying with a particular transition metal oxides, these layered niabates that were exfoliated, studying different transition metal oxide nanoparticles. When he got to rhodium, something funny happened, because the rhodium oxide nanoparticles are negatively charged at the pH where these colloids are stable, and they're also negatively charged. So they shouldn't stick to each other. But they had some very odd behavior. If you put in big crystals of this rhodium hydroxide, they would actually turn into little crystals and spread themselves all over the surface with 1 nanometer particles. It didn't matter what you started with. Start with the chloride, you get to these highly dispersed nanoparticles. And it turns out this happens with not just with rhodium, but with a bunch of different late transition metal halides and oxides. And so we're trying to figure out what's going on. And what's clear here is that this must be an energetically favorable process, because if you go from big particles to small particles, you have to overcome the surface energy that it takes to chop them up. And so the experiments we then did, this was Megan Strayer's work, was to use this wonderful technique of isothermal titration calorimetry to study to measure the bonding energy of these nanoparticles with these surfaces. And so this is a technique that's used widely by biochemists to study, for example, RNA folding and things like that, thermodynamics of biointeractions. We asked them if we could put our clays into their ITC, and they said, forget about it. So we then went over to Rob Ryu in chemical engineering. We said, we have this very dirty stuff to put into your expensive calorimeter. Can we do it? And he said, sure, no problem. We do that a lot. We're a catalysis group. We do that all the time. So we did these experiments with Rob's group, and I think in the context of understanding the thermochemistry of exfoliation and intercalation, which we still only have a pretty dim view of, these are very interesting experiments, because we can pick up little things like when we do this acid-base reaction, for example, that's a big heat in the ITC. So we could actually measure these interaction energies with different transition metal oxides. Some of them, like rhodium and especially iridium, are quite exothermic and make very small, very stable particles on these transition metal oxide supports. And this is pretty interesting for catalysis, potentially, for adhesion of one surface to another, and applications like that. So you can see, for example, in the case of iridium, we can deposit these 1 nanometer iridium oxide particles on these layered niabates and heat them up all the way to 1,000 degrees, and they don't really ripen. Whereas if you do that with an oxide that doesn't have this kind of strong interaction energy, then they start agglomerating right away. They're not prevented from becoming bigger particles. Okay. So an interesting question then is what's going on here? Why do these things resist agglomeration and bind so strongly in the case of late transition elements in, say, group 9 and group 10, but by the time we get to group 11 here with silver, it doesn't work. So what Megan Strayer, who worked on this, did was she measured these interaction heats with a bunch of different transition metal nanoparticles and a couple of different supports. So with this layered niobate support and with a clay or clay-like support, SiO2. And this plot shows this interaction heat plotted against this funny quantity, the heat of sublimation of the most stable oxide of the metal, minus the heat of formation of that, or rather the sublimation, sorry, this is the sublimation energy of the metal minus the heat of formation of the most stable oxide. Basically, this is something that scales as the metal-oxygen bond strength. So things that make stronger bonds to oxygen, like iridium, bind more strongly to the nanosheets. But they do it in an interesting way. That is, they care about what oxide they're bonding to. With a layered niobate, there's a strong trend. With a layered silicate, there's a weak trend. So we didn't really understand what was going on here, and we asked Mike Janik, who could do DFT calculations in the system, to think about this. And he did calculations not only on the systems that we had studied, but on many others that we didn't have data for yet. And interestingly, found the same trends. That is, not much change in bonding energy with silica support, but a big change, the same trend with the layered niabates. And so what's going on here? So there is actually a precedent for this kind of thing back in the old chemical literature. There are alloys of early and late transition metals that are very, very stable. So for example, zirconium makes a really stable alloy with platinum. Even though platinum is not a very reactive metal, it will react violently with finely powdered zirconium. And the explanation for this that came from Leo Brewer is platinum has too many d electrons to use them all effectively in bonding. Some of them are paired up. Zirconium has too few, but if you put them together, they have just the right number of d electrons to make a lot of d electron bonds. You can see this. This is some later experiments from Wayne Goodman, where he studied monolayers of metals like palladium on single crystals of other metals like tantalum, and measured the binding energy of carbon monoxide on these. Now, carbon monoxide will bond to palladium via a back bonding interaction. So if the tantalum, if you follow, is doing this, if the tantalum is taking away d electrons from the palladium, there's less d electron density in the palladium to back bond to CO, and so CO comes off at a lower temperature. And the trend they see in this kind of thing is that these early-late combinations have the weakest bonds to carbon monoxide. And also said they see shifts in core level bonding energies consistent with this. And in fact, that's exactly what's happening here. So if we take Mike's calculations and we look at the details of what's going on, what he finds is that in a very strongly interacting case like iridium with niobium, there is actually electron transfer from the iridium d orbitals to the empty niobium d orbitals, which happen to have their energies matched up pretty well. And if you try to do this with something like silver, the d electrons of silver are much more lower in energy, and so there's minimal energy overlap and minimal interaction here. So what's interesting here is we're really starting to get to the thermochemistry of these things, and these kinds of measurements are really starting to inform us about what holds layered solids together, what makes things stick to them, and you know, how we can maybe think about new chemistries to exfoliate and assemble other ones. So just some quick conclusions. I showed you a few different chemical exfoliation strategies for van der Waals solids and for intergrowth materials. Again, we have to tailor the chemistry for the kind of material we've got. But a little bit of chemistry, that is a little bit of opening the edges of the sheet, seems to be good enough if we combine that with physical exfoliation techniques to make quantitatively or nearly quantitatively single sheets out of a lot of different things like graphite and TMDs. Transition metal oxide nanosheets are particularly friendly for chemical exfoliation because we can combine ion exchange and acid-base interactions. And so all those interesting physical properties that I've mentioned on the first slide, like energy storage and superconductivity, et cetera, you know, we can start to think correlated electron effects that we see in oxides. We can start to think about making nanosheets that maybe do some of those things, or maybe a part of layered composites with graphene or 2D chalcogenides, et cetera. This layer-by-layer assembly works particularly well with charged sheets, but also with to some extent with van der Waals solids. And then finally, I just showed you this one case study where we can use calorimetry to really understand these kinds of interactions. So let me finally just thank the people I mentioned who had done this work. So I mentioned Hideo, who got us started on this with layered oxides and studying the binding of metal nanoparticles to them. Megan did the ITC measurements and worked with Tom Sentley, who was Mike Janik's student, and with Jason Bince, who was Rob's student, to study the electronic effects in these things. The exfoliation of graphite and BN was done by Nina Kofyakova, who tragically passed away just very recently, just a month or two ago. We're still working on Nina's last paper. Nina collaborated with Yuan Shi and with Vin and Mauricio and Nestor, whose picture I don't have up here, on characterizing these layered materials. And then finally, Xiaobin worked on the exfoliation of TMDs, and all that work is being continued now by Alyssa Rosas and Ritesh Upaluri, who are current students in the group. And I want to thank also our collaborators at NIST, who worked with us on electron microscopy, Jeff Miller, who worked with us on characterizing these nanoparticles on TMDs, and NSF and the Army for paying the bills. Thank you very much for your attention.
So before we go to questions in the room, we'll get some questions online. There are a couple in the queue already.
So the first question is it possible to control the morphology of 2D materials using exfoliation techniques?
Okay, yeah, that's an excellent question. So one of the challenges, of course, is to control these things in the lateral dimensions as well as in the third dimensions. So just in general, one can start with fairly large sheets, and the exfoliation strategies work with large sheets. But typically, the layer-by-layer assembly methods do not register the sheets with each other. That is, there's still this rotational degree of freedom that remains in the reassembled solid. There are one or two papers in the case of the oxides where restacking near equilibrium conditions will actually return the registry of those sheets, but those are rather rare examples. The other thing, the other kind of restacking that is interesting is scrolling or crumpling of the sheets. And there are strategies, I didn't have time to talk about them, but for many of these things, for making, for rolling them up, for making scrolls, and also for crumpling them and making balls out.
Second question is, what are the benefits of exfoliation techniques over other methods such as CVD growth?
Okay, so with basically with exfoliation, you can start with a bulk amount of material and end up with a bulk amount of material. So if you have an application where one monolayer isn't good enough, like let's say you're making a battery, then you really need you need more stuff than you can get with a monolayer. But of course, the CVD techniques and MBE techniques are becoming more and more sophisticated and make very clean, good layers of